All right. So, so any other questions on PA4? So this was a longer. Can we never do anything like that again? Uh, yeah, you could switch majors. Um, so here's the thing. This is much more typical of the kinds of assignments you're going to be getting into, right? So 223. So I call 222 the hardest course of the sequence, right? And it's hardest in part because it's a large leap from 121 and even 224. It's just a lot bigger step, right? We're kind of done spending energy and time on the fundamentals of C, and we're using C to do some fairly serious algorithms, um, like tree deletion. Um, so it's the most difficult course in that sense. But 223 is even more challenging than 222. 223, we're going to be working with a lot of different concepts. We're going to be doing networking. We're going to be doing multitasking and multi-threading. We're going to be dealing with objects. We're going to be making graphical interfaces. It's it's a lot more ambitious. The projects are a lot bigger, but they are a lot more fun. Um, we're not just building a command line interface that says insert this, insert that. We're doing stuff that actually does something. Making a game and making a chat program and things like that. Um, but the projects will be more along the lines of something with a lot of different pieces to it that need to be worked out and come together in a nice way, and it's very rewarding. um, don't feel like I can currently build anything useful with C. Oh, that's probably not true. I mean, we haven't worked with like a lot of packages that would let you do things like make something with a graphical interface or do networking or things like that. But you'll get to some of that stuff in future courses. Um, and we're building foundations. We're doing the gym work to have stuff to build on top of. So this was definitely an ambitious assignment, right? And my hope is that you come out of this with a better understanding of data structures, a better understanding of how um, you know allocating memory at runtime, how that's working, what that's all about, how to deal with in this function my license plate is always called plate, but it's not always the same plate because I did a malloc and I did a string copy, right? That kind of stuff. Um, so that's good. The grades were generally pretty low on this. I think the average was around 50 something. A lot of those point losses were probably avoidable though, right? And a lot of those grades would have been lower if I had graded strictly according to the grading rubric. So, for example, a large number of people did not put their name anywhere in the program, and I don't know what happened. The only thing I can find is that in the previous rubrics, I specifically said, a comment block in the beginning of main with your name. And in this rubric, I simply set a comment block in the beginning of main with name, comma, date, assignment number, etc. Um, but always put your name in your program, right? And we're getting to a point where you should be doing certain things whether or not I tell you to do them, whether or not there are point deductions for them. For example, if it says the program should be named plate, the executable, right? You shouldn't have to see a deduction in the rubric to decide I'm going to name it plate, right? If that's in the rubric, you should go ahead and name it. Now, I didn't take off points for that, but about a fifth of the class named their executable something different. And honestly, right, this is not just scare tactics. You go on to a university, your programs are either being graded by an automated system or, by a graduate student who's being paid, tuition breaks and has a few hundred assignments to grade. And they're going to take your repository, they're going to say make, they're going to say plate. If it says file not found, you're going to get a 0. They're not going to hunt around your make file and figure out what you named your program and rename it so they can run their automated script. They're going to smile inside because they got one less thing to grade now, and that's that, right? So you really want to try to do the best you can to follow the rubric. Whether or not, it's something that I stress in lecture, whether or not it's something that the grades, say you'll lose 5 points if you name the program wrong or something like that. Try to follow what's in the prompt as closely as possible. Double check everything, right? So a large number of people's make file had issues where if you say make, it should compile everything and build your executable. If you say make again, it should say, such and such is up to date. A lot of people's make files don't do that, okay? I stopped taking off for that and I went back and gave back points because so many people were doing this. If you call your executable program plate, you've got to tell the make file that what you're trying to build is called plate. If you tell the make file that the main target is main and you never make main, then every time you say make, it's going to try to rebuild it. So that's a simple thing, right? But after you say make again. Make sure that it says everything's up to date. And always, I'm seeing a lot of fancy make files. It's really cool. They're looking really good. Always, after you submit, make a new area, make a clone of your repository, go into that area, say make, execute your code, run your test cases, right? A lot of people lost 40 points because their program wouldn't compile, right? Sometimes it was because a comment got added and, there was 1 slash instead of 2 in the beginning of a comment. And that's it. Program won't compile. And again, if somebody's grading 300 assignments over the weekend and they say make and it says error, they're just going to write a 0 and go on, right? Now, I didn't do that. I ended up debugging a lot of students' programs. If you didn't include a function or you named the function wrong or you had a typo when you prototyped the function or something like that and your program wouldn't compile, right? In most cases, I tried to go in and fix those problems, right? So that I could grade the rest of your code and say, okay, yes, so 40 points off for the compile error, but your delete function works, your add works, that kind of stuff, right? So just double check that, right? Clone your directory, hop in, say make, say plate, database file name, make sure that works. It's really important down the road because, you may never talk to your professor. You may be working strictly through a TA, and if you thought the assignment was due at noon and it was due at 8, you're not going to get a lot of sympathy usually in most cases. Keep that in mind, right? And we'll keep moving things in that direction as we go forward. All of that aside, right? The code that people turned in was by and large really good. The delete function, obviously a lot of challenges around that, and I'm not worried about that. But most people, reading in the database, processing the command line arguments, building the tree, doing the searches, that all looked really good. Almost everybody nailed the traverse functions, which are straightforward but tricky to get just right. Almost everybody nailed those. What else? Yeah, so we spent a lot of effort in 224 parsing command line arguments and that kind of stuff, and I think most people got what they needed out of that. So I've been downplaying that a little bit in 222. I'd rather have you spending more of your time and energy on in this case data structures. So that's good. All right. So I gave you feedback on Canvas, and let me know if you have questions or want to talk about any of that. Um, cool. Yeah. So if recursion is making more sense, then this was a success, right? Because trees are all about recursion, and it's just kind of a good way to really kind of work more with those concepts. Um, so yeah, awesome. If that's starting to click more because of this, that's fantastic. All right. So any questions, comments, other comments? All right. So let's start talking about PA5. PA5 is due in a week. Okay. I don't want to have you turn this in at the end of next week because then we don't have a time to talk about it and so on. Um, so PA5 will be due a week from today. Um, it is a pretty straightforward project conceptually once we talk about it, but it's quirky. Okay, it's not something that's going to make sense if you haven't been to class and you're watching this on video and you're hoping that you're going to catch the idea of this in 10 minutes. That's not going to happen, right? We're gonna go through this today. We're going to talk about it for the next few days. We're going to do lots of examples of this kind of problem, and hopefully you're going to be working on this, throughout the week and asking questions and coming to office and so on. And you'll get there, okay? But it is a different kind of thing from possibly what most of us have programmed. Um, but it's a really cool class of problems. And there's a few pieces to this, but let me just start with the guts of it, which is something called the knapsack problem. So let me bring this up over here. All right, so here's the setup of the knapsack program. Um, you know how sometimes stores have these events where you're the 1 millionth customer, and so you win some kind of prize, right? And typically the prize is a shopping spree. So here's the setup. You've just won this shopping spree, okay? And the deal is, they give you a bag, and you're allowed to fill this bag with whatever you want, and whatever you can fit in the bag, you can keep. And you've got like an hour to do this, and the cameras are following you around and all this good stuff. And the bag is limited by weight, not by size. Okay, so you have a bag that can hold, say, 25 pounds worth of stuff, and you're allowed to put anything you want in the bag as long as it's no more than 25 pounds. And the question is, how do you extract the maximum value out of that arrangement? And so you have a table of items that might look something like this. So this is a store that only sells 4 things, right? There's a mouse, which is worth $5 and weighs 1 pound. These are bogus units. There's a cell phone that's worth $100 and weighs 2 pounds. There's a tablet that weighs 5 pounds and is worth $200, and there's a laptop that weighs 10 pounds and is worth $1,000. And if your bag could hold 100 pounds, what would you put in there to get the maximum value, assuming you're just going to go to eBay and sell this stuff, right? So how would you maximize this, right? So probably 10 laptops would be your winner. That would be $10,000. That's going to be far better than putting in 20 tablets, which would only be worth $40,000, and so on. Yeah, or unobtainium. I think if you fill a 100-pound bag with californium, you get a good neighbor check from the Men in Black. Yeah, you could sell the knapsack too. because it probably says stuff on the side. All right, so how do we do this? This is a trickier algorithm than you might think to come up with. So we'll talk about the algorithm in a few minutes, but the program, right, you're going to write a program called knapsack. It takes two arguments: the capacity of the bag and the name of an item file, okay, which will have something like this. And this is a set of triples with the name of an item, the value, and the weight. These are integers. This is a string with no spaces, so it's easy to parse, right? And your program should basically figure out a solution to this knapsack problem and then print out something like this. So here's sample code you can run on the server. So there's a file under temp called knapsack. There's an item file called knapsack.data. And if you run this with a capacity of 21, okay, so my program, it echoes the contents of the item file, just so you can see. Tells you the bag's capacity, tells you the highest possible value is 800, and the way to do that is to take 4 phones, which was item 3. All right, and a lot of this is boilerplate stuff, right? So make sure that the person puts in exactly 2 arguments. The first argument is an integer, usual error checking. You can assume that there are no more than 128 items to deal with. So this file is limited to 128 lines, which means you can make static arrays of 128 elements for storing this information. And you can assume the maximum bag capacity you'll be given is 1024. And these will simplify your coding. You can also assume that the name of the item is no more than 32 characters and that there's no spaces in there. So those all make life a little easier. And make a GitLab repo named, well, I called it knappack. So I'm going to stick with that even though that's a typo. Call it knappack. Otherwise I'll be in trouble if I change it. So make a repo with that name. And the grading is pretty straightforward, right? So yeah, that's the quirky part, right? All right, so if I don't get your repo by 8 a.m. Monday, it's no points. And I'm not going to take late submissions on this because this will be week 10 and we'll have SLP presentations going and all kinds of stuff. So no wiggle room on that, right? 8 a.m. And as usual, if you make your repo before 8 a.m. tomorrow, I'll be happy to download it, and or before noon tomorrow, I'll be happy to download it and tell you if I can access it. If your program doesn't compile, that's at least 50 points off. If there's warnings, that's 10. Seg faults when I run it, 50. If it doesn't give a solution, that's 50 points off. If it gives a solution but it's not an optimal solution, that's 30 points off. If it takes forever to run, that's 30 points off. And this is the second part of what we're going to talk about, is how we make this thing run efficiently. And that's using something called dynamic programming. And if it doesn't report, how many of each item get me that solution, or if the count is incorrect, that's 15 points off. If this works, you know that it works, right? You can run it against test files, you can compare it to the sample code, and if it works, right? I'm not going to nickel and dime you on formatting of your output, but I want all this information. I want a copy of the item list, I want the bag's capacity, I want the maximum value, and I want a list of items showing me how many of each item get me that value. What would short count as? A short amount of time. You'll know it when you see it, right? If we do dynamic programming with this, it will basically come back immediately. If you don't, you'll sit there for, minutes or hours, and there's a good chance your machine will crash. So, we'll see that. All right, so let's dig into the knapsack problem. And this example was pretty straightforward because the laptop is so much more valuable than any other thing. This is worth, $5 a pound. This is worth $50 a pound. This is worth $100 a pound. right? So as much laptop as you can get, that's going to be your winning solution. And if this was a you know, like a food co-op where you had big bins of stuff and you could just pull out, you know, however many pounds and ounces and fractions of an ounce you wanted, right? Then there's a greedy algorithm that will solve this problem, which is figure out the value of each item per pound or per unit weight and take as much of the most valuable item as possible. And if you have an unlimited supply of laptops, right, we would just fill our bag with laptops. Now, if our bag could hold 11 pounds, right, and this was, you know, a bin of bulk laptop, we could get 1.1, or, you know, we could take 1.1 laptops, right, and maximize. But it's an integer knapsack problem. You can only take whole numbers of these things. So that's one complication. And because of that, a greedy algorithm is not always going to work. So let me give you an example. I actually worked one out ahead of time. So let's make a table of let's do weight and value. Let's look at the value per weight. And I don't know, I'll put a name on here. So let's have item 1, it weighs 3, it's worth $9. Item 2 weighs 4 and is worth $13. And item 3 weighs 2 and is worth $1. So this is, you know, a pen. And this is, you know, I don't know, a book. And this is ink. Yeah. All right. So 3 pounds for $9, 4 pounds for $13, 2 pounds for $1. So what is the pen worth per unit weight? It's worth, you know, 50 cents per pound. The ink is worth $3 per pound. The book is worth $3.25 per pound. So this is clearly your most valuable item. And, you know, if you had a 40-pound bag, you would want to take 10 books. But suppose your capacity is equal to 6. So a greedy algorithm would do the following. It would say take one book, which weighs 4 pounds and is worth $13. And then we have 2 pounds left while we can take a pen, which weighs 2 pounds and is worth $1. And so your bag ends up being worth $14. But there's a better solution to this problem. So what's the better way to fill your 6-pound bag? 2 inks. So a greedy algorithm is an algorithm that works by doing the best solution you can at each step. In this case, if you're trying to maximize the value of the bag, at each step we make the decision that maximizes the value of the bag so far, which means fill it with as much of the most valuable item. That does not work for the integer knapsack problem. So we need a different approach. And right, this is happening because, you know, if we put in the 4-pound item, we only have space left for this really invaluable item. Whereas by giving up a little bit of initial value by taking an ink, we have enough space for another one of these items, and that ends up being worth more. So we need to do something a little fancier here. something like recursion. So let's make some arrays, and let's store the weight and value of each item. So this is your inventory, and what we call an item list in the assignment. And we're going to define a function called maxVal. And this function returns the maximum value possible with a bag capacity. Let me call this cap. So max value, give it a bag capacity, it gives you back the maximum value that you can get from a bag with that capacity. And how do we write this function? It's really, really simple conceptually. So here's what we want to return. And this is going to be pseudocode. We're going to return the largest of the following calculations. So what is this? Suppose that you have an empty bag with this much capacity. And suppose you place item 1 in that bag. Okay, you've committed that you're going to put item 1 in that bag. So you have one copy of item 1 in your bag. You've done two things. You've added this much value to your bag, and you've diminished the capacity of the bag by this much. In other words, you know, if our bag can hold some capacity and I put one of item 0 in our bag, well, now I have, you know, $9 worth of value in my bag, and my bag can hold 3 pounds less than it could originally. So this is the new capacity of my bag. This is how much value I got from putting in item 0. So how much value can I extract from this remaining capacity? Well, my maxVal function will tell me that. So maxVal is going to calculate the best that I can get with this remaining capacity, and I'm going to add the value of that first item I put in. That will tell me my maximum value if I start by putting item 0 in my bag. On the other hand, I might start by putting item 1, in which case I get the value of item 1, and I diminish the capacity of my bag by the weight of item 1. Or I could start with item 2, and I diminish my capacity by the weight of item 2. So all my maxVal function has to do is return the largest of these 3 calculations. So that's a very high-level view of this algorithm. And there's details we need to worry about. But does that basic direction make sense so far? And we're going to work with a number of problems this week related to this that are all going to have a similar kind of algorithmic solution, where we're trying to define a function, and we define it in terms of, you know, some other call of that function. In effect, it's comparing all possible combinations. It will get through all possible combinations, but we're not sort of writing this by thinking about that. And if we were to simply go through and find, all combinations, we would probably end up doing more work. And this will be a little more tactical. And it's forcing us to use this idea of recursion in actually, formulating this algorithm. But logically, we have to start with some item in the bag, and depending on which item we start, one of these will tell us the maximum value. And so if we just find the largest of these three, that's our answer for max val of cap. And as always, recursion has to end somewhere. And in this case, that's on these recursive calls. Max val is only defined for a capacity that is bigger than 0. All right, so here's one caveat. If cap equals 0, return 0. So if your bag can't hold anything, the maximum value you can get out of that is 0. The other thing is, when you call max val, right, only call max val if your capacity minus weight is not negative, right? This is the value I can get out of my bag, assuming I start by putting item 0 in my bag. Well, if item 0 weighs more than the capacity in my bag, don't calculate this value. Don't take that into account. Don't compare it to the others. Right? This is not meaningful if we can't put item 0 in our bag. This is not meaningful if we can't put item 1 in our bag. So in your logic where you're calculating these and comparing them to find the largest, you need to make sure that you check first to see if this item will actually fit in that bag. And if it doesn't, don't do that calculation. And you can't short circuit that by just saying if capacity is less than or equal to 0, return 0. Because then you're still assuming that you can fit that item in that bag. All right, so let's do an example of this. Capacity equals 6. So to find the maximum value from a bag of capacity 6, we want to calculate the largest of three things. The value of the first item plus, and let me just call this MV, max val. So it's the value of the first item plus the maximum value of our capacity minus the weight of that first item. Or it could be 13 plus the max val of our capacity minus the weight of that second item. Or it could be 1 plus the max val of our capacity minus the weight of the third item. You could do greater than 0 or greater than or equal to 0. The way I've written it will simplify your code a little bit, but if it makes more sense to do greater than, you can do that. You just need to make sure that if you don't calculate anything, you know what value to return, which would be a 0. All right, so we need to calculate max val of 3, max val of 2, max val of 5. and these are going to be recursive. So max val of 3 will be equal to, well, the value of the first item plus the max val of 3 diminished by the weight of that item, which is 0. So it's going to be the largest of either that or, well, we could try to put item 4 in, but item 4 won't fit, so we won't calculate that. But we could put item 3 in, which gets us a value of 1, plus the max val of 3 minus 2 is 1. So that's max val of 3. And we need to find max val of 2. And max val of 2, well, we can't fit items 0 or 1 in, but we could fit in item 2. So it's 1 plus the max val of 0. Max val of 1, well, we can't fit anything in a bag with capacity 1, so this is 0. Max val of 0 is 0. And we also needed to calculate max val of 5. So that's the largest of the following. So 9 plus max val of 2, or 13 plus max val of 1, or 1 plus max val of 3. So, you know, max val of 3 will calculate 9 plus max val of 0, and 1 plus max val of 1. Well, we found out what these are, so this will be 9, this will equal 1, and so max val 3 is equal to 9. Max val 2 is 1 plus max val of 0, so this is equal to 1, this is 0, this is 0. Max val 5 is equal to the largest of these, and we already found max val 2 is 1. Max val 1 is 0, and max val 3 is 9. And so the largest of these is 13. And so our final answer for max val of 6 is either 9 plus max val of 3. Max val of 3 is 9. Or 13 plus max val 2, which is 1. Or 1 plus max val 5, which is 13. And the largest of those is 18. So that's the maximum value of a bag of capacity 6. And you might note that we never calculated max val of 4. I don't know why that is. Oh, that should have been a 2. Because we diminished, right, our item 3 weighs 2. So we should have calculated max val of 4. So we have to do some other steps. Okay, cool. And when we're done, we'll end up with an 18. So this is a highly recursive formula, right? But that makes it easy, relatively easy to code. So your whole guts of your program really comes down to one function, which is just max val. And it takes an integer capacity and it returns an integer, which is the maximum value for that capacity. And it's pretty much a single loop. that loops through each item in your inventory, and for each item calculates the value of that item plus the max val of your bag when you decrease the capacity by the weight of that item. And to find the maximum of these, what do? Well, you initialize something equal to this, and then you loop through the rest. And if your sum is bigger than what you initialized to this, then you save that as the new maximum value. So it's like doing a running sum or something, but it's a running maximum. And make sure you're not calling this when your weight is bigger than the capacity of your bag, so you're not counting negative things. And that's most of what you need algorithmically to get the max value function to work. And then there's two additional complications. The first one's not bad. The first one is this is going to be really slow. You're going to end up calculating values again and again and again. Right, for example, here we had to use max value 1, here we had to use max value 1, here we had to use max value 1, and so on. So we're going to need to speed up the recursion, and that's what dynamic programming is all about. And that's basically caching your recursive call results, and we'll play with that tomorrow in detail. The other piece to this that's more tricky is when you're done, you want to know more than just the maximum value. You don't just want to know I can get $18 out. You want an actual list of items that you put into your bag to get that $18. So you need to keep track of more than just the maximum value. You also need to know what items should you use to get that maximum value. And so you're going to need to come up with a data structure for storing that information and being able to pass it around. And it can be as simple as, an array of structures where each element tells you how many of a certain item you have, right? So here I've got a solution that came from having, one of these and one of these. Or when I made this call to max val, my solution involved using 2 of these. And then you adjust those item tallies accordingly based on which item you're adding to your bag. So we'll go through some examples of that also. But that's the other part of this is returning the actual inventory of what items you put in and how many of each item to get that maximum value. All right, so that's a quick first pass through PA5. If you're anxious to get started on it, I would say start with trying the sample code, which is on the Linux server, so it's under /temp. Play around with that, get an idea, make your own knapsack files, and play around with those to look at some of the edge cases and so on. And then, write something that will ingest that file, so that's going to be, easier than what you did for PA4 reading the license plate database. And you can just use static arrays because we've limited the inventory to 128 items. So you need 128 names, 128 values, and 128 weights. So you can make all of that static. And then, the guts of the program, start working on a max val problem solution. All right, so we'll continue with this tomorrow. I will see you next time.